Okay, so hello everyone. In this video, we will cover disk architecture and scheduling algorithms. So in this video, first we will discuss architecture of hard disk and then discuss scheduling algorithm like FCFS, SSTF, scan and look. These are very simple and important algorithms. So let's start with introduction to disk architecture. We are going to discuss disk architecture today, and this is an important topic because this also comes in operating system, computer organization and various other subjects related to storage. Now let's start with understanding what disk architecture actually is. First of all, I would like to tell you that the architecture of disk is divided into a specific sequence, and this sequence is itself you have to remember properly. First of all, what we have are platters. The platters are circular, flat disk, and you can have multiple platters in single hard disk. So these platters are connected together with something called a spindle. Now, what is the work of this spindle? The spindle is used to make all the platters move together. It means either the spindle will rotate clockwise or it will rotate anti-clockwise, but it will be unidirectional, meaning it will consistently move in one direction only. So as soon as the spindle start moving, all platters will start moving together at the same speed and the same direction. Each platter is like a circular disc, and if you want to visualize this better, think of it like old CDs or DVDs that we used to have. The shape of the structure is quite similar to those CDs. Now, surface and read-write heads. What is there above every platter? This is a surface, upper surface and a lower surface. We use both the upper and lower surfaces of every platter for storing data. Now, what's there above these platters? Above these platters, we have read-write heads. What do we call these? Read-write heads, which are connected to an actuator arm. You can call it just arm or actuator arm. What is the job of these read-write heads? The job of read-write head is to fetch data. These are used to read data from the disk and also to write data onto the disk. Their movements is very specific. It's only back and forth. This means their movement is possible only backward or forward in straight line. Since I am using both the surfaces, upper surface as well as lower surface, the actuator arm will be designed in such a way that it can read the upper surface as well as the lower surface simultaneously. If you want to visualize this better, in movies many times they show gramophones. What a gramophone has is a black circular record which they place on the turntable, and then they put a needle on it and like music start playing. That needle which moves over the record is similar to our read-write head, and the black record is similar to our platter. If I talk about this platter, what is there on this platter? There are tracks. There are tracks on this platter. These tracks are circular lines and are made on a platter surface. Obviously, if tracks are these on the upper surface, then there will also be tracks on the lower surface. The same number of tracks will be on the upper surface and the same number of tracks on the lower surface. Now, the read-write head that we have is positioned on any one of these tracks at any given time. Let's say I have to go to any inner track. As I have already told you, the read-write head can move either forward or backward only. It cannot move in any other direction. The disk itself can rotate, but the read-write head will either go forward towards internal tracks or backward toward external tracks. Internal tracks are the inner ones and external tracks are outer ones. Now, what actually is there on each track? On each track you have sectors. These sectors are like small division on segments of the track. So the next thing we get in our sequence is sectors. On every track we have sectors. There are fixed number of sectors on each track. Let's say there are 256 sectors on each track. This means how many sectors we have on every track is 256, whether it's upper or lower surface. Now, what do we do inside these sectors? Inside these sectors we put the data. So the next and final thing we get is data, which we store inside these sectors. So this sequence you should be familiar with: platters, surface, tracks, sectors and data. So if they ask what is the total disk size or disk capacity, you multiply platter into surface into tracks into sector into data per sector. Now moving forward, disk access time components. Now let's move to the disk access time, which is crucial for understanding disk performance. There are several time components involved when accessing data from a disk. The first and most important time is seek time. What is seek time? Seek time is the time taken by the read-write head to reach the desired track. Let me explain this with our disk architecture knowledge. We have multiple tracks on each surface and the read-write head will be positioned on some track initially. Now let's say my data is stored on a completely different track. I need to bring the read-write head from its own current position to a track where my data is stored. The time taken is in the movement is called seek time. Now what can be the best case scenario? In the best case, your read-write head is already on the track from where data needs to be picked up. What can be the worst case? You are on the outermost track and you go into the innermost track or let's say vice versa. Since we cannot predict exactly where the head will be, we usually take the average case. What does average case mean? On an average, you will have to move half the number of tracks to reach your desired track. Seek time is the most important component among all the time components we are going to discuss, because this creates the maximum delay. If we can reduce the seek time, the overall performance will improve significantly, because that reduction directly decreases the latency. Now the next time is rotation time and rotational latency. The second component is rotation time. Rotation time is the time taken for one full rotation on the disk, which is 360 degree. Now you might ask, why do we need rotation? Let me explain with an example. We have reached the desired track using seek time, but now what? Let's say this is my desired track. What's inside this track? Inside the track we have multiple sectors. After reaching the correct track, we need to reach the correct sector within that track. Since the disk is constantly rotating, we need to wait for the desired sector to come under the read-write head. This is where rotation time becomes important. Rotational latency, also called as rotational delay, is the time taken to reach the desired sector within the track. Typically half of the rotation time. Why half? Again, we take the average case. In the best case, the desired sector is the right under the read-write head when we reach the track. In the worst case, we just miss the sector and have to wait for one complete rotation. On average, we wait for half of a rotation. So this is rotational latency. Now what is transfer time? The third component is transfer time. Transfer time is calculated as transfer time is equal to data to be transferred divided by transfer rate. The amount of data will be given in the question. It might be like the data from the one sector, two sector, or multiple sectors. The transfer rate is how much data can be transferred per second. Sometimes you are not directly given the transfer rate and you need to calculate it. The formula for transfer rate or data rate is transfer rate is equal to number of heads into capacity of one track into number of rotations per second. Now let me explain each component. Number of heads, this means the number of surface. If you have 4 platters, you have 8 surface, so 8 heads. Second is capacity of one track. You can find this multiplying the number of sectors in one track by the data capacity of each sector. Now the next one is number of rotation per second. This is often given as RPM, rotation per minute. If you get 3000 RPM, you divide by 60 to get rotation per second. 3000 divided by 60 is equal to 50 rotation per second. So that was all about the times in disk architecture. Now moving forward to controller time and queue time. Sometimes controller time is also given. The controller is like a software or a driver that controls the entire disk architecture. If controller time is mentioned in the question, you simply add it in your total time. If it's not given, you don't need to consider it. There is also a queue time. Since disks are slower than CPU, sometimes multiple requests come to disk simultaneously. These requests are stored in a buffer or queue and they wait for their turn. So this is what? This is queue time. Now total disk access time. What is the total disk access time? The total disk access time is seek time plus rotational latency plus transfer time plus controller time if given or queue time if given. Among these, the first 3 components, seek time, rotational latency and transfer time, are the most important and will be present in most of the question. The last 2 are optional and depend on the specific question. Now let's move to the disk scheduling algorithm. The goal of disk scheduling algorithm is to minimize the seek time, thereby improving the overall performance of the disk system. Now the first algorithm is FCFS, first come first serve. Now let's understand this with a practical example. Disk contains 200 tracks numbered 0 to 199. Request queue contains track number 82, 170, 43, 140 and 24 and 16 and 190. This is our request queue. Now in every algorithm we will take this same question as our example because we have to understand the algorithm first. So this is our request queue. Now current position of read-write head is 50. In FCFS, first come first serve, we simply service the request in order they arrived. So our sequence will be 50, then 82, then 170, then 43, then 140, then 24, then 16, then 190. To calculate the total track movement, we find the difference between consecutive position. So if we are at 50, what is the first value arrived? 82. So as shown on the screen, we move our head towards 82, then 170, then 43, then 140, then 24, then 16 and then 190. So we have followed the order first come first serve. Now to calculate the total track movement, so you can either calculate like 82 minus 50 plus 170 minus 82 plus 170 minus 43 plus 140 minus 43 plus 140 minus 24 plus 24 minus 16 plus 190 minus 16. You can calculate this way, but you can calculate also it like you can see the direction. Where the direction has changed, you can take that much time. So to calculate the total track movements, we find the difference between consecutive positions. So total movement is equal to 642. Notice that the read-write head follows a zigzag path because requests are scattered across the disk. First come first serve is no starvation. Every request gets service in the order it arrived. Second is simple to implement. It is simple to implement. And the third one is fair to all requests. It is fair to all requests. Now what is the disadvantage? Poor performance due to excessive head movement. No optimization for reducing seek time. It can result in very long seek times if requests are randomly distributed. Now moving forward to shortest seek time first, SSTF. In SSTF we always move to the nearest stack first regardless of arrival order of request. In this question we are simply starting from position 50. Let's see which request is nearest. Distance to 82 minus 50 is equal to 32. Distance to 170 is equal to 120. Distance to 43 is equal to 7. It is the smallest. And distance to 140 is equal to 90. So we go to 43 first because it is smallest. From 43, which is the nearest, distance to 24 is smallest. So we will go to 24 next. From 24 nearest is 16. From 16 nearest is 82. Then 142. Then 170. And then finally 190. So our sequence become 50 to 43. Then 24. Then 16. Then 82. Then 140. Then 170. Then 190. To calculate total movements, it will be 50 minus 16. We will calculate it directionally. So you can see it on screen in diagram that we are moving to 50 to 16. We are not changing any direction. So 50 minus 16 plus 190 minus 16 because we are not changing any direction. So it will be 34 plus 174 is equal to 208. So this is much better than first come first serve. Now what are the advantages of SSTF? Better performance than FCFS. It reduces average seek time and it has also good response time for most requests. Now what are the disadvantages? Starvation problem. If a request keep coming for the middle tracks, request at the edges of the disk might wait. So this is the problem of starvation. Now what is the problem of overhead? Need to calculate the distance for all pending requests at each steps. So these are the disadvantages of SSTF. Now moving forward to scan algorithm, SCAN, scan algorithm. Scan algorithm is also called the elevator algorithm because it works like an elevator. The read-write head moves in one direction until it reaches the end, then reverse direction. So using our same example with direction towards larger values, it is given in the question that our direction is towards larger values. We are at 50, so we will go at 82, then 140, then 170, then 190. So it is our last request, but we have to go to end of the disk 199. So we will go to the 199 and then we will go from 199 to 43, then 24, then 16. In scan algorithm, the key point is that even though our last request in the upward direction is 190, we still go to 199, the end of the disk. Now total movements is equal to what? 199 minus 50 plus 199 minus 16. This will be 149 plus 183. This will be 332. Now what are the advantages of scan algorithm? No starvation, reasonable performance, predictable behavior. These are the advantages of scan algorithm. Now what are the disadvantages of scan? Unnecessary movement to the disk ends, request at the edge might wait longer. So this is the disadvantage of scan algorithm. Now moving forward to look algorithm. Look is similar to scan but more efficient. Instead of going to very end of the disk, it only goes to a last sequence in that direction. So we will first go from 50 to 82, then 140, then 170, then 190, then 43, then 24 and then 16. So this will be our sequence in look algorithm. Now notice here one point. We stopped at 190, last request. Instead of going 199, we have stopped at 190. Now what are the total movements? 190 minus 50 plus 190 minus 16. So it will be 140 plus 174 is equal to 314. Now this is better than scan because we avoid unnecessary movement to the disk end. Now moving forward to C scan, circular scan. What is circular scan? C scan treats the disk as circular. It moves in one direction, then jumps to opposite end and continues the same direction. So first we will go from 50 to 82, then 140, then 170, then 190, then 199, and from 199 we will go to 0. From 0 we will again go to 16, then 24, then 43. The jump from 199 to 0 represents the circular nature. We do count this movement in our calculation. Total movements is 199 minus 50 plus 199 minus 0 plus 43 minus 0 is equal to 149 plus 199 plus 43 will be equal to 391. Now if we look at C look, what is circular look? So C look is like C scan but jumps only from the last request in one direction to the first request in the opposite direction. We will go from 50 to 82, 82, then 82 to 140, then 170, then 190, and from 190 we will go from 190 to 16, and then we will go to 24, then we will go to 43. So the total movements will be 190 minus 50 plus 190 minus 16 plus 43 minus 16, so it will be equal to 341. So that was all about disk architecture, and we have seen all the algorithms. But what are the important points to remember? Architecture sequence: first platters, then surface, then tracks, then sector, then data, and then seek time is usually the dominant factor in disk access time. Now power of 2 are commonly used in capacity calculation, and FCFS prevents starvation but has poor performance. SSTF has good average performance but can cause starvation. Scan and C-scan provides fair service but may have unnecessary movement. Look and C-look are more efficient version of scan and C-scan. Always count head movements even when jumping from one end to another in circular algorithms. When solving numerical problems, it's helpful to represent tracks linearly 0, 2 and -1. Even though they are actually circular on the physical disk, this makes calculation easier. So that's it for this video. We will meet in next video. Until then, bye bye.